All right, so we have our generalized eigenvalue problem. This is the thing that we are going to spend most of class time solving and playing around with some actual data. So I just want to say a few more things before the end here. Oh, come on. Okay. All right, so this is the thing we want to solve, and we will do so in class. But the thing that comes out of it are these eigenvalues lambda. And you can show, and I'll give you a reference that talks about this a little bit, that you can write down an effective energy, which is essentially like an effective mass, that looks like the log of this eigenvalue. Note that lambda should also depend on T naught, because for every different T naught that you have, you'll have a different eigenvalue lambda. So if you look at the log of this lambda and we look at a lattice time derivative, so just a lattice finite difference like you would do for an effective mass, then you can show that the energy that you're looking for, just as you would expect with an effective mass, is what this function will approach for large times. Okay, and to do that, we're going to assume that we're in some time where only a finite number of states contribute. And in particular, I want to have only some number, capital N, states contributing. So we look at some time region where only, say, 4 states are believed to contribute to the correlation function. And then, so that means that our correlation function matrix, we should be able to write as the sum of only up to capital N states of the exponential of the energy times some overlap factor. So the overlap factors here, psi, these correspond to the overlap between the nth eigenstate wave function and the Jth operator that was in my correlation function matrix. Okay, I'm now going to define dual vectors. And duals are just a mathy way of saying the thing that when I multiply my vector by gives me 1 for the Kronecker delta. So it's basically a dual vector is like a dual to a column vector is a row vector, for example. So it's the thing that you multiply by in order to get a scalar number. And these n and m have to be less than or equal to big N, because I'm only looking in the space where these n states contribute. Okay. So I can now apply my correlation matrix onto my dual vector un. And when I do that using this orthogonality here, I get that it picks off the psi n with e to the minus en. And then using my generalized eigenvalue problem, this is also equal to my lambdas. Okay, so basically I've just said that I know that C acting on V gives me lambda C of T naught times V. So when I apply C to my dual vector U and also use this orthogonality constraint, I get on the right hand side the same relation but with my U's. But now from this, so using that these lambdas are related to these exponentials of the energy, this implies that my lambdas go like e to the minus en times t minus t naught. So this is kind of like the recursion relation that we saw when we talked about matrix pruning. Okay, and then the final thing that I wanted to say, and I want to give you a reference for this so that you can read where this is shown, but the corrections from the higher states, so by higher I mean larger than the big N that I assumed contributed, right? Because only at infinite time can you ever say that only a single state contributes, and that's always a ground state, unless you have exact orthogonalization. So these corrections scale as e to the minus delta this e that I'll define in a second times t. So delta e sub m, where m is not equal to n, is just the energy difference between the m and the nth state. So the corrections to the higher states that you haven't, due to the higher states that you haven't included, are going to scale with the gap between the next energy and whatever energy level you're looking at. So if you allow yourself to have more than, what do I want to say? If you include more operators in your basis for your matrix Cij, then you can diagonalize and find more of these eigenvectors, and that increases the number n that you can assume are contributing, and therefore as n gets bigger and bigger, this energy difference will also get bigger and bigger for some given fixed state n that you're interested in, and therefore the corrections will become smaller and smaller exponentially. Okay, so we will discuss this way more in detail in class, and I'm also going to give you a few questions to answer now, and hopefully you will have questions for me as well.